Thank you very much, Rudiger, for your fun jokes. And hi, everyone. And thank you. First of all, I would like to thank all of you for coming here at this late hour of the day just to listen my and also Nicolas' talk today. And for me, it's a great pleasure to present my inaugural lecture here. Lecture tonight, bringing generative AI and reinforcement learning towards safer and brighter future to this wonderful crowd here. And so, as most of you know, like AI models are grabbing headlines every day, and it's getting into our lives and day to day. And most of us, I'm pretty sure, already started using like large language models, for example, like ChatGPT, GPT-4. And many people think about like GPT-4 as a conversational agent, but like it's more than that actually. You can use it to write your code. You can use it to create spreadsheets. You can even like use it to plan your next holiday vacation destination. And a second group of like generative models or like AI models that we know, and I'm pretty sure many of you are familiar, are like multimodal generative models. For example, Midjourney is one example where you can provide a text prompt just to generate an image. And finally, in AI for science, like another success of like these AI models is basically very well-known AlphaFold, where you can basically use like to fold proteins with very high precision, and like it's being like getting into toolbox of biologists like to kind of like to use it for especially for drug discovery. However, we are not there yet. Despite the great and impressive success of deep learning and AI systems, they still have flaws and they still have a long way to go, basically. The existing algorithms still need to be fixed and can sometimes fail unpredictably on relatively simple tasks, as you can see on the screen. In particular, these mistakes can be unacceptable in the real-world situations, where safety-critical applications, like for example, AI for science, where you need high precision, or like if you are deploying into the real world, where many millions of people will probably using, then you don't want these mistakes in your application. So this opens up an important research direction that we need to address. So the ethics of AI and doing responsible AI research is an important emerging topic. And in particular, like poorly studied and poorly understood methods when deployed into real world can cause like serious troubles. For example, if you have a medical diagnosis agent, and if you want like medical diagnosis, and if it once in a while if it makes mistakes, then it can have catastrophic consequences on people's life if they are assigned to wrong diagnosis or wrong medication. And in 2017, Microsoft trained a chat agent on Reddit mostly, and then they deployed it on Twitter. And people start poking it and asking questions, and like they immediately, within a couple of hours, managed to expose like some extremely toxic and racist behaviors of this agent. And similar problems are emerging with like the agents like ChatGPT and Gemini as well these days. One of the downsides of these models is basically they are very large and slow as well. As these models getting deployed into real world, applications like Apple Siri, Google Search, or YouTube, it raises important concerns with respect to carbon footprints and impact of them on the climate as well. Their energy and power consumption is one of the main costs of for the cloud compute centers. And for example, to address that, Microsoft is actually basically like planning to create like nuclear power plant just to power their AI operations. However, there is still hope. And the focus of my lecture is basically going to be on how to address some of these issues and basically some baby steps towards that direction. All these issues that we discussed and that I will discuss today are very interesting and important research questions that needs to be addressed and studied carefully. In the last few years, we have been seeing lots of very impactful research being done, improving model efficiency, for example. And for example, like in the last couple of weeks, there was this one paper that showed that actually you can train 7 billion models, which would take like tens of GPUs to train before in just one single GPU. And in terms of safety and biases, the models are much safer than before, actually. Thanks to mostly curated data sets and new training paradigms, alignment, and debiases method. But there is still a lot to do. So RL is core to most of the research problems that I'm kind of like exploring in my lab. So let me give you a very quick introduction to reinforcement learning, just like in a few slides only. RL is all about like decision-making and sequentially decision-making, basically. In the sense of reinforcement learning, it's all about like trial and error. It's similar to what we do all the time. We try things. If they work, we do it again. If they don't work, we try something else. Now let's look into this like simple RL example. We have a humanoid robot, and we are in the simulation environment where the robot is trying to learn to do parkour. And basically, after 200 trials, it cannot even stand still, as you can see. However, after 1,500 trials, you can see that like, it can just like run through the parkour without any problems. The key takeaway here is that we did not handcraft the solution, and we did not show or tell the agent what the solution would look like. We just like provide a goal by providing a reward function to the agent, and the agent discovered the solution on its own. And just like purely from trial and error. And there are two important aspects to the paradigm. Firstly, because learning operates by trial and error, it allows us to specify the goal of the learning process rather than the solution directly. And like, it allows us to discover solutions that we couldn't come up with ourselves. Secondly, it can deal with long-term dependencies and delayed reward and delayed feedback. Rather than just looking into immediate reward, agent can learn basically by choosing actions that leads to higher reward in the long term. This is obviously an important property for learning in the real world. We often need to do things that can make us like worse off in the short term, but will lead to good outcomes in the long term. Now, deep reinforcement learning, which is one of the main topics of this presentation, has started making impact in real world as well. And some of the successes that I will show here is basically, many of you probably know like AlphaZero and AlphaGo, where an agent can achieve like superhuman performances on chess and Go. And now we are starting to see like the impact of like these reinforcement learning agents making on the robotics domain. And RL can solve a kind of like multi-agent, highly stochastic environments like StarCraft as well. And many generative AI algorithms like ChatGPT also makes strong use of like RL for alignment and safety purposes. And we started seeing that like RL is like started making impact in the real world as well. In a collaboration with DeepMind and EPFL, we know that like now we can use reinforcement learning to control fusion tokamak reactors as well. So as you can see, like RL is coming a long way and slowly getting out of the simulations to make an impact in real world. Now I will give a quick overview of what foundation models are. And foundation models are basically a very popular way of like modeling the sequences And as you may notice from the name, basically they lay the foundations for other approaches. And I'm pretty sure like many of you are familiar with these large language models. Like we already discussed about ChatGPT, but Claude and Gemini as well. There is a belief that suggests that like these are mythical beasts, but like they are, and that no one really understands, like Pokemons. However, that's completely incorrect. These are algorithms and models that we coded ourselves, and someone knows what the data distribution looks like, although most of these commercial models are completely closed. But if we have the access to the data and the weights, we can actually study them and understand them, basically. They are far from mythical beasts. And there is a very strong research agenda going now at the moment at EPFL and all over the world to understand these models better. And foundation models are, you can think of them as like massive data regurgitators. So they can take any type of data, let's say text, audio, vision, and they represent in this like neural network representation layers. And then they can map it to other data modalities like text, audio, vision. So you can map from one data distribution into another data distribution. Now here I show a brief history of some of the most prominent foundation models. You can see that the number of new models coming up each year is just like growing rapidly. I excluded 2024 on purpose because like just like in a couple of months, there were like almost 100 like different models that came up. And it made the slide look very messy, so I just like removed it. But you can see the amount of interest on these models at the moment. And it's not only the number of new models coming up each day, but like historically, if you look at the data, like you can see that actually the number of parameters of the models are growing as well. For example, machine learning models around 50s, like they used to double the number of parameters every almost like 2 years. But like between 2018 and 2011, the number of parameters doubles every 4 to 8 months, basically. Now, like I just like made this like very basic plot. Basically, I took the peak teraflop of different GPUs released by NVIDIA, and the peak teraflops is basically a quantity that tells you how fast like these like GPU chips can be on running these AI models, basically. So it's a very rough metric, but like it's at least like for illustration purposes, like it gives a good insight. And you can see that like the kind of like the peak teraflops, the performance of the models grows exponentially if you fit an exponential curve. And if you extrapolate to see what will happen in 10 years, you can see that like from 1,000 in 10 years, it goes up to 80,000 peak teraflops. But there are two important features with the GPUs that determines the number of like peak teraflops that you can squeeze into them. One of them is the transistor size limit, and the other one like the number of cores limit. Of course, like you can come up other features as well, but I just list here the most important ones. And the transistor size limit is bounded by the kind of like the radius of the silicon atom. And the number of cores limit also kind of like is limited by the kind of like the, is limited as well in terms of like performance. Now, according to estimates, we will reach the limit for the transistor size in 2030. And for the number of cores limit, without hurting the performance, we'll reach around 2033 for the GPUs. So what happens next? One possibility is, of course, like we'll turn the whole planet into a large GPU cluster. That would be ridiculous. But of course, like there are other alternatives. People like Sam Altman looking into raising $7 trillion right now, just like to invest into new hardware. But the other alternative that I'm interested in my lab is basically making these models more efficient. And so one main important building block for these models is basically transformer architecture. So there is like kind of like, it has been super popular and more or less like all the foundation models or large language models that we discuss use this architecture. One big advantage of this architecture is that it's super easy to parallelize. However, there are some downsides, like it's slow to train, and as a result, it's slow to deploy as well. And it requires like tons of data to train on. The reason it's slow to train and slow to deploy is basically because the transformer layer, each block, basically learns to compute attention over all the inputs, basically. And that makes it very slow, especially at the deployment. And deployment is actually very important because like the main cost, again, of these like models is actually lies when you kind of like serve them to the masses, to the public. Like when you serve ChatGPT, suddenly millions of like people start using, and compared to training, actually, inference is much important for these models. In our recent work, so I will talk about one of our recent work on Griffin, building efficient foundation models. So in our recent work, we propose an alternative architecture to transformers, and kind of like there are two different models here. And they both like make use of an old paradigm in machine learning called recurrent neural networks. And they can be both like efficient at training, but also efficient at deployment, but also scalable as well. To be more precise, like two architectures that we introduce here are called Hawk and Griffin. Hawk is basically a pure recurrent neural network model based on just like the idea that I mentioned on like recurrent neural networks. This is even simpler because like there's no nonlinearity. It's just like pure linear RNN with some form of gating, and you apply only the nonlinearity at the output of the network. And the other model is basically called Griffin. And Griffin is a hybrid model, so that's why it's called Griffin. It includes one local attention per every two recurrent layers, basically. Now, it's important to conduct proper scaling law analysis on these models to understand their performance, how they change with respect to allocation of like more resources and more compute as well. So we scale both Hawk and Griffin to 7B and 14B, and it was unprecedented for this family of models to scale to that size. And both models, like similar to transformers, they exhibit like power law scaling curves. And Griffin actually achieves like slightly lower held-out loss or validation loss compared to very strong baseline transformer that we tested and compared against. And Hawk, also pure recurrent neural network model, also closes the gap as we scale the training flops. And so how about inference, right? So I mentioned that inference can be costly, and it can be actually one of the main bottlenecks. So there's one metric to pay attention here. It's called throughput. Throughput stands for maximum number of tokens that you can decode from these models per second. And during inference, both Hawk and Griffin achieve lower latency, but also much lower throughput as well. And when sampling, especially when sampling very long sequences, and you can see for context window of 4,000, actually Hawk model is like 14 times faster here. And so one reason why the throughput is so important here is basically for reinforcement learning, especially for RL and alignment or safety. Actually, one of the main bottlenecks is in the throughput and sampling time. And if you look at the downstream evaluations, Both models that we propose here have like finite state size, meaning that like kind of like your state doesn't depend on the context length or the sequence length. And they both like provide fast inference, as I just mentioned. And also, they also have efficient training on device as well. For longer sequences, you can train it faster with custom implementations. And on downstream performance, we show that like excellent performance on downstream tasks, as you can see in the table. But scaling doesn't solve all the problems magically. We also need the post-training. And for that, like one topic I'll be discussing here, which I'm very excited about, is the alignment. Alignment is basically an algorithmic approach to align models, outputs of LLM with the human values to make them safer. And so what is alignment? What alignment achieves is basically, given the model M, or let's say you have a foundation model, it tries to align the output of this foundation model to maximize the score assigned by the reward model R. And the reward model here is basically, it can be the preferences collected from humans directly, or it can be a model that learns human preferences from the data. And naturally, this can be framed as a reinforcement learning problem. And typically, we push like, by doing that, we push AI systems towards like, towards aligning with the human's intended goals or preferences or ethical preferences. So if you look at the stages of training an LLM, there are like two main stages. The first stage is like pre-training. On pre-training stage, we train the model on more or less everything that we found on the whole internet. And during the fine-tuning, there are two steps. Like first, like instruction fine-tuning, where we just like basically collect a small subset of like supervised data, and we fine-tune our model on this small set of like supervised data to be able to make them better at conversing with humans. And in the final alignment stage, as I mentioned, like we have the reward model, and we use that reward model to align the policy or our model, generative model itself. And in the alignment, basically we try to make the models safer and like align with the human's intended goals. And this becomes more important as we scale the models like to be larger and larger. And regarding to that, I'll discuss about our work called Reinforced Self-Training that proposes a very simple kind of like approach for that. And there are basically two different steps into REST algorithm. The first step is basically growth step. You start like kind of like in the growth step, you take the model and you just like start sampling from the model to generate a synthetic data. And so you create your own data set from the samples using the model. And then in the inner loop, you do, like once you are done with the growth step, you start doing improvements on that data. So in our paper, we explore different types of improvement steps. But like the one that worked the best, like Occam Razor is like completely kind of like valid here. The simplest algorithm that we could think of basically worked the best. And we thought it will be initially a baseline for our models, but that was the approach that worked the best, which was basically taking the reward model and just like using it to rank the outputs and discarding the ones that don't kind of like have higher scores basically. So it's a very basic filtering scheme. So you filter your data, and then you fine-tune your policy on the filtered data that you know high quality with respect to your reward model. And the nice thing is like it's purely offline, and it's super easy to implement. It's super efficient as well. And so the nice thing is like it works great as well. So we tested on several different translation-based baselines, data sets. We focus on mainly English to German, German to English, and Chinese to English because Google Translate team thought that those are the most interesting language pairs that they would like to improve on. And we show like consistent improvements on several benchmark data sets for these language pairs, as well as like Google's internal data set called Web Domain for English to Chinese as well. And recently there have been a couple of papers that came up and used more or less the same algorithm, but applying on math and reasoning tasks. And they showed like very promising or state-of-art results on math tasks, basically, and reasoning tasks. So going back to the lab and the goal, there are kind of like 3 pillars I see. The first pillar is like efficiency, how we can make these algorithms more efficient, both in terms of compute, but in terms of sample as well. And this efficiency pillar interacts with like the other pillars very tightly as well. And the second, robustness and safety pillar, the goal there is basically how to make these models like safer, for example, by using like RL and alignment-based approaches. And the final pillar is basically using reinforcement learning to act in the noisy environments and or like using reinforcement learning to do better reasoning or discovery. And as the title suggests here, RL and efficient foundation models is at the heart of the lab. And there are 2 kind of like use cases like currently we are considering. One for basically RL for efficient foundation models, where the goal is basically to do alignment for safety, as well as discovery and better reasoning. And the second goal is basically the efficient foundation models for RL, for example, for robotics or other domains, like to improve the exploration, to get better representations, or to do better credit assignment. And this is the first row is the lab, and the second row, basically some of the collaborators that work with me on some of the papers that I mentioned. And I sincerely thank them, and finally I thank all of you for attending this talk. I hope you enjoyed and learned something.